This is P. Mabuhussain, Assistant Professor of EEE, Institute of Aeronautical Engineering, Hyderabad. Today, in this video, we are going to explain about the numerical problems on inductance of single circuit as well as double circuit transmission line. So, the learning outcomes of this lecture is that by the end of this lecture, the students will be able to calculate the inductance of three-phase single circuit transmission line, in which the conductors are arranged either symmetrically or asymmetrically or on a horizontal plane. Symmetrically in the sense that the three conductors will be at equal distances, equal spacing will be there between the conductors. Asymmetrically in the sense, so the distance between the two conductors is not same, so which is called the unequal spacing between the conductors. Even if the conductors are placed on a horizontal plane, so then if you observe the distance between any two conductors, then also there will be unequal spacing between the conductors. In all the three cases, we will find the inductance of a transmission line system, and also we'll calculate the inductance of double circuit line in case of unsymmetrically spaced line as well as on a horizontal plane. So to calculate the inductance of either single circuit or double circuit lines, we need to remember some of the important equations here. Suppose if the transmission line is a single phase transmission line, so then the inductance for the single phase transmission line per each conductor and per meter will be calculated by using the formula 2 into 10 power minus 7 ln dm by ds. And dm here is the mutual GMD, and the mutual GMD will be the distance between the two conductors, which is small d. Suppose if you are having the two conductors here in the transmission line system, and the distance between these two conductors from center to center is small d. So then in such a case, the mutual GMD here will be the this d only, so which is the spacing between the conductors. And self GMD of each conductors will be calculated by using the expression 0.7788 times the r, which is nothing but the value of self GMD ds will be equal to r dash. So that value is 0.7788 times the radius of conductor. Okay, so this is the equation for calculating the inductance of a single phase transmission line for each conductor and per meter length. So in a similar way, if you are having a single circuit transmission line, so the single circuit transmission line in the sense, also in a three-phase system, you will be having only one set of three phases, right? So A, B, C. This is one set of three phases. So if you are having one set of three phases in such type of transmission line is called a single circuit three-phase transmission line system. Now for such type of lines, the inductance can be determined by using the expression 2 into 10 power minus 7 ln dm by ds. So this will be same as the first equation itself, but the value of dm and ds will be different here. So the value of dm, which is the mutual GMD, you can calculate. So by using the expression d1, d2, d3 whole to the power of 1 by 3. This is the equivalent equilateral spacing, right? So which is called the d equivalent also. So right. So what is this d1, d2, d3 here is nothing but, so these are the distances between the two conductors in the three-phase transmission line system. So if suppose between A and B, the distance may be d1, between B and C, the distance may be d2, and between C and A, the distance may be d3. These distances we have to consider for calculating the mutual GMD of a single circuit three-phase transmission line system. And the self GMD. So self GMD here will be same as the r dash. That r dash is the 0.7788 times the radius of conductor. Okay, so this is the equation for calculating the inductance of each phase per meter length in a single circuit three-phase transmission line system. Now if you are having a double circuit three-phase transmission line system, in a double circuit three-phase transmission line system, you will be having a two sets of three-phase conductors. That means you will be having one set of three-phase conductors like A, B, C. Another set of three-phase conductors will be in the reverse direction, A dash, B dash, C dash. So this is one set of three-phase conductor. This is another set of the three-phase conductor. So such type of transmission line is called a double circuit three-phase transmission line system. Now in double circuit three-phase transmission line system, the inductance in each phase and per meter length will be calculated by using the expression 2 into 10 power minus 7 ln dm by ds. Here the value of dm and ds will be different, right? So dm will be calculated by using the expression dab, dbc and dca whole to the power of 1 by 3. Now here dab is nothing but this is the mutual GMD between the conductors A and B. Okay, and dbc is the mutual GMD between the conductors B and C, and DC is the mutual conductor between the conductor C and A. And the overall mutual GMD in case of a double circuit transmission line system will be DAB into DBC into DCA whole to the power of 1 by 3. Okay. So now for calculating the self GMD also, we need to calculate the self GMD of each conductor. So self GMD of each conductor will be DS1, DS2, DS3. So these we have to calculate, and whole to the power of 1 by 3 you have to consider. So the equivalent DS value for a double circuit transmission line will be DS1, DS2, DS3 whole to the power of 1 by 3. So DS1 is the self GMD of conductor 1 in section 1. DS2 is the self GMD of same conductor in the second section, and DS3 is the self GMD of conductor 3 in the same section. Right. So these are the formulas which we need to remember for calculating the inductance of any type of transmission line, whether it is a single phase transmission line or single circuit 3-phase transmission line or double circuit 3-phase transmission line. So in all the cases, the main formula will be the same. So to the calculation of inductance, the main formula, if you observe, the value is 2 into 10 power minus 7 ln dm by ds only. So but only the value of dm and ds calculation only different. Okay. So in single circuit transmission line, dm will be the same as the distance between the two conductors. And in a single circuit 3-phase transmission line, the value of dm will be d1, d2, d3 whole to the power of 1 by 3, so which is same as the d equivalent, which is equilateral spacing. And the value of dm in case of 3-phase double circuit transmission line will be dab, dbc, dca whole to the power of 1 by 3, where dab, dbc, dca are the mutual GMDs again. Okay. So on the DS value, if you observe, the DS for a single phase transmission line as well as a single circuit 3-phase transmission line will be the same. So 0.7789 times R value. And for a double circuit transmission, this will be equal to DS1 into DS2 into DS3 whole to the power of 1 by 3. So these are DS1, DS2, DS3 are the self GMD of the conductors in each section, if you consider a transposed transmission line system. Okay. So now let us see the problems for a double circuit as well as single circuit transmission line here. So the first problem here. So find the inductance per kilometer of a 3-phase transmission line using 1.24 centimeter diameter conductors when these are placed at the corners of an equilateral triangle of each side 2 meters. Here you have a 3-phase transmission line, and in this 3-phase transmission line, the conductors are arranged at the corners of an equilateral triangle. An equilateral triangle in the sense the distance between any 2 phases will be the same, right, which is 2 meters. It was given here, right? So 2 meters is the distance between any 2 conductors. This is 2 meters, this is 2 meters, and this is also 2 meters. So which is nothing but D1, D2 and D3. All values will be same. Okay. And also given that diameter of each conductor will be 1.24 centimeters. So then from this radius you can find out by dividing with 2, which is 0.62 centimeters. Here you are getting the conductor radius, which is 0.62 centimeter. Now in this case, the calculation of inductance equation, if you observe, so then the inductance per each phase per meter length here. So per meter length will be 2 into 10 power minus 7 ln dm by ds. Now here the value of dm will be d1, d2, d3 whole to the power of 1 by 3, and the value of ds is 0.7788 times the R value. Right. Now you have to calculate the value of dm and ds by using these expression. Right. So now ds value is equal to 0.7788 times the R value. Right. So now here you have to substitute the value of R, and what is the value of ds you see. So 0.7788 times into R value here is the 0.62. Okay. So now if you calculate the 0.7788 multiplied with 0.62, you will get 0.4828. Okay. So this is the ds value. So then in similar way you calculate the dm. So by using the expression d1, d2, d3 whole to the power of 1 by 3. So now here d1, d2, d3 as the distance between 2 conductors in a 3-phase systems. Right. If you observe all the 3 phases A, B, C here, the distance between any 2 conductors will be the same. D1, D2, D3 all will be equal to 2 meters. So this will be equal to 2 into 2 into 2 whole to the power of 1 by 3. So which is 2 cubed whole to the power of 1 by 3. So 3 will get cancelled. So dm value will be 2. Okay. So dm value will be 2 meters. Okay. And ds value here is in centimeters. Right. So now while calculating the inductance here, so by using this expression, the value of dm as well as the value of ds both must be in the same unit. Now here if you observe, the value of ds is in centimeters and the value of dm here is in meters. So you have to convert any one of these two into the same unit. Right? I am converting this dm into centimeters, so that 2 into 10 square centimeters you will get, which is 200 centimeters. Okay. So then the inductance per phase of its three-phase transmission line will be 2 into 10 power minus 7 into ln dm by ds. Right, now substitute the value of dm and ds here, so that you will get the value of inductance per each phase. So this value is 2 into 10 power minus 7 ln dm. So dm value is 200 centimeters by ds value here is 0.4828. 0.4828. Okay. So now if you calculate this value, you will get the inductance per phase per 1 meter. Right. So that value is 12 into 10 power minus 7 henries. Okay. So this value if you calculate, you will get 12 into 10 power minus 7 henries. So this is for 1 meter. Right. If you want to get for 1 kilometer, so then you have to multiply this with the 1000, so that you will get the value of inductance in kilometers. So henries per kilometer you will get. Okay. So this even can be written as 1.2 into 10 power minus 3 henries, which is equal to 1.2 millihenries. Right. This is how you can calculate the inductance of a single circuit 3-phase transmission line system. Right. A single circuit 3-phase transmission line system, in the sense here in a 3-phase transmission line you will be having only one set of 3-phase conductors. Right. Now here the distance between any two conductors is given as the same, which is the symmetrical spacing is given here. So then you can calculate the inductance in this way. Right. So now let us see another problem. Here the 3-phase conductors in a transmission line system are arranged at the corners of a triangle. So on the triangle sides are given as 2 meters, 2.5 meters and 4.5 meters. Right, here you have to take a 3-phase transmission line in which you will be having 3 conductors, and here they are giving that the distance between any 2 conductors is not same here. Right. Suppose if it may be d1, which is equal to 4.5 centimeters, and it may be d2, so which is equal to 2 meters. This is in meters, sorry. Right, and d3 value is given as 2.5 meters. Right, d1, d2, d3. So they are given as different values. So this is the unsymmetrical spacing of conductors. Right. So the distance between any 2 conductors is not same here. So this is the configuration of unsymmetrical spacing of conductors. Okay. Now in this case you have to find out the inductance of this transmission line per kilometer. So when the conductors are regularly transposed. Here when the conductors are placed unsymmetrically, in such a case you have to use the transposition of conductors for getting the average inductance to be the same in each phase. Suppose if you are not doing the transposition of conductors, so then if you calculate the inductance for each phase, the value of inductance for each phase will be a different value. Okay, so that you will get the unbalanced voltage at the receiving end. So to get the balanced receiving end voltage, you need to transpose the transmission line in case of a unsymmetrical transmission line system. Right, here they are saying that the conductors are regularly transposed. So when the conductors are regularly transposed, in such a case the inductance of each phase will be the same here. The value of LA, LB, LC, all inductances are same, so that if you calculate one value, you will get the all values here. Okay. And they are also giving that the diameter of each conductor to be 1.24 centimeters. Right. So now let us see here. So the value of D1, D2 and D3. Right. They are considered to be D1 to be 2 meters, D2 is 2.5 meters and D3 4.5 meters they are considering, right? So here this is D3 and here this is D1, this is D2, like that they are considering here. Now the conductor radius if you want, then here the diameter is given, which is 1.24 centimeters. Now if you divide with the 2, you will get the radius of each conductor. The radius of each conductor R is equal to 1.24 by 2. So then you calculate this value, will get 0.62 centimeters here. Okay. So now for this case, the inductance per phase per meter length will be calculated by using the expression 2 into 10 power minus 7 ln dm by ds here. Again on dm and ds you can calculate by using these two expressions. So ds is the 0.7788 times the R value here. So ds is equal to 0.7788 times into R value here is 0.62. So if you calculate this value, you will get 0.4828 centimeters. Okay, this is in centimeter. Now you can calculate the value of mutual GMD by using the expression d1, d2, d3 whole to the power of 1 by 3 here. Now the value of d1 is 2 meters and the value of d2 is 2.5 meters and the value of d3 here is 4.5 meters. So you have to calculate dm value here. So which is the expression d1, d2, d3 whole to the power of 1 by 3 and the value of d1 here is 2 meters and the value of d2 here is 2.5 meters and the value of d3 is 4.5 meters whole to the power of 1 by 3 you will get here. Okay. So now you do calculate this value. So what is the value you will get? 2 into 2.5 into 2 into 2.5 into 4.5 whole to the power of 1 by 3. Now if you calculate this value, you are getting the value to be 2.823. So this value is in meters, right? Because all these here are in meters only. So 2.823 meters you will get the value of dm, right? So now if you this meters you have to convert into centimeters. So for converting meters into centimeters, you have to multiply with 100. Okay. So then if you multiply this value with 100, so then 282.3 centimeters you will get. Right. Now you got the value of dm as well as ds. So then the inductance per phase in a three-phase transmission line system you can calculate by using the expression 2 into 10 power minus 7 into ln dm by ds. Here the value of dm is 282. So 2 into 10 power minus 7 ln. So dm is 282 by ds value is 0.4828. So here 0.4828 you will get. Right. So now if you calculate this value, you will get the value of inductance per each phase. Right. If you the value to be equal to 12.74 into 10 to the power of minus 7 henries, you are getting this value is for 1 meter. Okay, henries per meter here. Right. And the other phases also will be having the same inductance. Why? Because these conductors are transposed at the regular intervals. Right. So inductance of phase B as well as inductance of phase C also will be the same. The value is 12.474 into 10 to the power minus 7 henries per meter. So now this value you have to calculate for 1 kilometer length of the transmission line. So you have to multiply this with 1000 so that you will get the value of inductance in kilometers. Right? 12 into 12.74 into 10 to the power of minus 4 you will get. So minus 4 henries per kilometer. Right? This even can be written as 1.274 milli henries per kilometer. Right? So like this we can calculate the inductance of a three-phase single circuit transmission line system in which the conductors are arranged asymmetrically. Okay. Right. So now let us see the problem of a three-phase transmission line system in which the conductors are arranged on a horizontal plane. Okay. So when they are arranged on the horizontal plane, in such a case, the value of two distances may be the same, but it is not same as the last distance. Okay. If you see here, the conductors 1, 2 and 3. So distance between the conductors 1 and 2, D12 as well as D23. So this value may be the same. So but it is not equal to the D31. So because of that reason, this transmission line also will be considered as a unsymmetrical transmission line system, right? So to calculate the inductance for this unsymmetrical transmission line, you have to use the same procedure what we have done in the previous problem. So let us see how to calculate the value here. Okay. So if you read the problem once, so to calculate the inductance of each conductor in a three-wire system, when the conductors are arranged in a horizontal plane with spacing such that the value of D31, so D31 is 4 meters and D12 and D23 will be 2 meters and 2 meters. Okay. Now here the conductors are transposed and have the diameter of 2.5 centimeters, right? As this configuration is a unsymmetrical configuration, to get the value of inductance same in each phase, you have to transpose the transmission line at regular intervals, right? So they are saying the problem that the conductors are transposed. So when the conductors are transposed, inductance in each phase will be the same. So the inductance of one phase, if you calculate, that will be same as for the other phase also. Okay, and the diameter of this each conductor is given as 2.5 centimeter. So let us see here. So when the diameter is given, the radius of the conductor will be calculated by dividing the diameter with the 2. So the radius of conductor then R is equal to 2.5 by 2. Okay, then you will get 1.25 centimeters as the radius of each conductor. So then the inductance per phase per meter length you can calculate by using the expression 2 into 10 power minus 7 ln dm by ds here, right? And the value of ds is same as 0.7788 r, and the value of dm is underscore cube root of d12, d23, d31, right? So this is same as the previous one, d1, d2, d3 whole to the power of 1 by 3. Here instead of d1 they are saying d12, instead of d2 they are saying t3, instead of d3 they are saying d31, like that. Okay, so the equation is same as the previous one only, so don't get confused here. So only the distances they are represented as d12, d23, d31. So I'm using this expression for calculating the value of dm here. Okay, right? So now the value of dm here is cube root of and d12 and d23. So these two are 2 meters and 2 meters. So 2 into 2, and the value of d31 is 4 meters, which is given in the problem itself, right? So now if you calculate this value, the value of dm you are getting here is 2.52 meters, right? Now this dm value which is in meters, you have to convert into centimeters by multiplying with 100, right? If you multiply with 100, so then you will get the 252 centimeters, right? So then the value of ds you can calculate by using the expression 0.7788 times the r. Here the value of r is 1.25 centimeters. So you substitute here 0.7788 into 1.25, right? So now you calculate the this value 0.7788 multiplied by 1.25. Okay, so this value you are getting 0.9735 centimeters. Okay, now you got the ds value as well as dm value. You substitute it in this expression to calculate the inductance per phase per meter length. Okay, so here I will calculate the value of inductance per phase, any phase A or B or C. So all values will be the same because the conductors are transposed here. So this will be equal to 2 into 10 power minus 7 ln dm by ds, and the value is in henries and for 1 meter length only. Okay, so 2 into 10 power minus 7, and the value of dm here is 252. So ln 252 by, so ds is 0.9735. So you substitute here 0.9735. Now you calculate this value with the calculator, so that you will get the value of inductance per phase in henries per meter length. So that value you are getting here is 11.1 into 10 power minus 7 henries per meter length. Okay, this is the inductance per each phase per 1 meter length only, right? So now here in the problem they ask to find out the inductance of each conductor in kilometers, right? So if you want in kilometers, so then this may be multiplied with the 1000, so that you will get the value of inductance in henries per kilometer, right? So 11.1 into 10 power minus 7, if you multiply with 1000, so then the value of inductance is 1.11 into 10 power minus 7 henries. So that value is 1.11 millihenries. So this is the value of inductance per each phase per kilometer. Okay, so millihenries is in for each kilometer. Okay, this is how you can calculate the inductance of a three-phase unsymmetrical transmission line as well as a single circuit transmission line in which the conductors are arranged on a horizontal plane. Okay, right. Till now we discussed the calculation of inductance of a three-phase transmission line by considering a single circuit transmission line system. So in three cases, when the conductors are placed equilaterally, so that means if the distance between the any two conductors is same, so then how we can calculate the inductance. And if the distance between any two conductors is not same, which is unsymmetrical spacing of conductor, so then also we calculated the inductance. And if the conductors are arranged on a horizontal plane, so then also we calculated the inductance for a single circuit three-phase transmission line system. Now let us see for a for that same three-phase single circuit transmission line system, if the conductors in each phase are bundled conductors, in such a case how you can determine the inductance. Let us see. Okay, so a single circuit three-phase transposed transmission lines is composed of two ACSR conductors per each phase. Okay, so with the horizontal configuration which is shown in the figure here. So find the inductance. So here they are asking the inductance X. Okay, so per kilometer at 50 H, and radius of each subconductor in the bundle is given as 1.725 centimeter. Right. So here if you observe the figure here, it is a single circuit transmission line system. Why? Because here you have only one set of three phases. Right. This is phase A you can consider, and this is phase B, and this is phase C. So but each phase is having two subconductors, right? So phase A is having two subconductors, A and A dash, and phase B is having two subconductors, B and B dash. C also having two subconductors, C and C dash. Okay, so here in each phase we are using a ACSR conductors, and this ACSR conductor is composed of two conductors in each phase. Okay, so now the each subconductor radius is given here. The radius of each subconductor is 1.725 centimeters. So that means this is having a radius of 1.725 centimeters, and this is also having the radius of 1.725 centimeters. Like that, all B, B dash, C, C dash, all the subconductors are also having the same value, 1.725 centimeters. Okay, so now here they are also given the distance between two subconductors, which is 0.5 meters. Okay, in a each phase you are having two subconductors. So between the two subconductor, the distance is represented with a small d, and that d value is also given, which is 0.5 meters. Okay, now here you have to calculate the inductance. So the inductance X is here is you can calculate by the expression WL. Right, for calculating the inductance, you need to find out the inductive reactance. So not inductive reactance. They ask to find out the inductance only. Right. So when they are asked to find out the inductive reactance, you can use X is equal to omega L. So here omega is 2 pi F into L here. So F is given as 50 here. So you can even calculate the inductive reactance by using this expression. Okay. So for calculating the inductive reactance here, first you need to find out the inductance per kilometer length of the transmission line. Right. After that, you can calculate the inductive reactance here. Okay. So let us see how we can solve this problem. Okay. So inductance per phase per meter length for calculating the transmission line inductance will be 2 into 10 power minus 7 ln dm by ds. The expression will be the same for any case. So, but only the value of dm and ds will be different here. Okay. So now the value of dm you can calculate by using the expression dab, dbc, dca whole to the power of 1 by 3. Okay. So dab here is the distance between phase A and B from center to center. Similarly, dpc is the distance between phase B and C from center to center. So dca also the distance between the conductors, not conductors, the phases between C and A here, right? So center to center distance you have to consider, right? So now center to center distance, if you observe here, so this distance, so they are given it to be 6 meters, and this center to center distance, this is given as also 6 meters, and from here to here the distance will be 12 meters. Okay, so DAB is 6 meters and DBC is 6 meters and DCA here is 12 meters you will get. Okay, so just simply substitute all the values here in this expression. So dm is equal to 6 into 12 whole to the power of 1 by 3. Okay, so then what is the value you are getting here? So once you calculate 6 into 12 whole to the power of 1 by 3. So then this value will get 7.55. So 7.55 meters. Okay, this is one procedure. Okay, so by considering the center to center distance, so then dm value you can calculate by using this expression dab, dbc, dca whole to the power of 1 by 3. So then you will get the value of dm to be equal to 7.55 meters. Okay, so better to use this this procedure only, because other procedure is somewhat difficult, not much difficult, but it is the easy way. Okay, so if you want to calculate in another way also, I will tell you. Okay, so DAB here is the mutual GMD by considering the phases A and B here. Okay, so you have to consider the phase A and phase B. Phase A and phase B you have to consider. So then you have to find out the mutual GMD between the phases A and B, right? So while calculating the mutual GMD for phases A and B, you have to consider all the mutual distances. Mutual distances here is, if you consider A, so DAB distance, DAB distance is one mutual distance. Then DAB dash is another mutual distance. So then if you consider A dash here, DA dash B is one distance, DA dash B dash is another distance, whole to the power of 1 by each phase how many conductors you are having, the multiplication you have to take. Here also 2 subconductors, here also 2 conductors. So 2 into 2, 4 will be the denominator here, right? So now then if you see here, what is the value of DAB, what is the value of DAB dash, what is the value of DA dash B, you have to calculate here. Okay, so DAB here, if you see, so DAB is from here to here distance. Well, this is same as capital D here. Okay, DAB is capital D. Now if you see the A to B dash here, so then here the value will be equal to D plus D here. Okay, so D plus D here. So how you are taking, I will show you again. See here. So from center to center, the distance is capital D. Okay. Now if you adjust this up to here, so now from here to here, you will get the same, which is capital D. Okay. So DAB is, you are getting capital D. Now DA to B dash, if you see, so DA to B dash here is this D plus this small d. So D plus D you will get. Similarly, so A to B, if you observe, so this distance. So this distance is this total distance D minus small d. Okay. So in similar way, so D A dash B dash from here to here. So the distance if you see, so that the distance will be the same, which is capital D whole to the power of 1 by 4. Okay. And the value of capital D here is 6 meters. So 6 into 6 plus D here is 0.5 meter. So 0.5 into 6 minus 0.5 into 6 whole to the power of 1 by 4. So this value is 6 into 6.5 into 5.5 into 6 whole to the power of 1 by 4 you will get. Now if you calculate this value, you will get DAB to be equal to, so DAB here is nothing but mutual GMD, right? So DAB will get 5.989 meters. Okay. So now in a similar way, you have to calculate DBC and you have to calculate DCA also. So if you calculate DBC, so then DBC also you will get the same value, so which is 1.989 meters, and DCA if you calculate, the value will get 11.994 meters. Right. Now the value of DM will be this value multiplied by the this value DAB, DBC and DCA, all the values whole to the power of 1 by 3 if you will take, you will get 7.549 meters here. Okay. So this is another procedure, but this is a bit difficult to calculate. So instead of using this procedure, you can use the procedure which I told before, right? In which you will consider DM to be equal to the distance between faces AB, distance between BC, distance between CA. So these distances whole to the power of 1 by 3. Here DAB we will consider to be equal to center to center distance between A and B faces, right? So center to center distance which is 6, right? DBC center to center distance is again 6. DCA center to center distance is total 12 whole to the power of 1 by 3. So then if you calculate, you will get 7.55 meters, right? This 7.55 meters and this value both will be the same. So better to use this procedure instead of the previous procedure, which takes the more time. Okay, then if you use this procedure, it will take the very less time and you can calculate within short period of time. Okay, so this is how you can determine the mutual GMD in two way. So you can, if you comfortable with any other method, you can use any one of them. So right, I will prefer this method here. Okay, so then the value of DS. So DS here is the self GMD, and this self GMD you have to calculate for each phase. Right now, if you observe the each phase it is having 2 conductors. So the self GMD while calculating, you have to consider all the distances in each phase, right? So conductors A and B you are having, A and A dash you are having the phase A, and all possible products of distances will be DAA, then DAA dash, then DA dash A dash, then DA dash A whole to the power of 1 by, so how many conductors you are having, whole square you have to take, as here 2 are there, so 2 square you have to take. Now here the value of DAA and the value of DA dash A dash, these are the self distances. So this value will be equal to R dash. Okay, so this R dash is 0.7788 times the R here. So this value is equal to 0.7788 times the R value you can take here. So we will do it later, right? You remember that the value of DAA, DA dash A dash will be equal to 0.7788 times the value of R, or simply R dash. Okay, you substitute here in this equation. So DS is equal to DAA here is R dash, DA to A dash distance if you see, this is small d, and DA dash A dash again R dash, DA dash to A distance is small d whole to the power of 1 by 4 you will get. So this will be R dash D whole square whole to the power of 1 by 4. So which is same as R dash D whole to the power of 1 by 2 you will get. Okay, so the value of DS here is R dash d whole to the power of 1 by 2, and the value of r dash here is 0.7788 times the value of r here. So here we are taking 0.778 times, and the value of r is 1.725. Okay, so this value you will get in centimeters. So but the value of d here is 0.5 meters is given. So we are converting this r dash into meters by dividing with 100, right? So then you are multiplying with 0.5 whole to the power of 1 by 2. So the value you are getting it to be 0.0819 meters. Okay, so this is the value of ds in meter, and the value of dm in meters is 7.55 meters. So the inductance per each phase will be calculated by using the expression 2 into 10 power minus 7 ln dm by ds, and dm here is 7.55, or if you use another procedure you are getting 7.549. Okay, you can take any one. So by 0.0819, so here 0.0819 is the ds value. If you calculate this value, so then you will get the value in henries per meter, right? And if you multiply that with 100, you will get the value in henries per kilometer. And finally, if you calculate the inductance value, the value of inductance you are getting here is 0.904 millihenries per kilometer. Okay, so this is how you can determine the inductance of a single circuit 3-phase transmission line, in which each phase is having bundled conductors, right? Here we consider the 2-phase bundle. Even if you consider the 3-phase or 3-conductor or 4-conductor bundle also, you have to use the same procedure. Okay,
like, share and subscribe. Hit the bell icon for more updates.